In this lecture, we are going to look at sensors, transducers, signal conditioning, and methods that are used to connect sensor units to controllers. Let's begin by looking at sensors, transducers, and signal conditioning. A sensor or a transducer is a device that changes a physical quantity into an electrical quantity. This change is necessary because, in general, control systems are electrical in nature. Therefore, they require inputs into them to be electrical in nature. Sensors and transducers thus serve this purpose. Typical physical quantities that are usually inputs into control systems include temperature, light intensity, displacement, weight, and speed, amongst many others. When such physical quantities are sensed, they produce corresponding electrical quantities such as a corresponding voltage, a corresponding current, a corresponding resistance change, an inductance, a corresponding capacitance, or a corresponding frequency. A sensor is made from a material that exhibits a particular variation on some electrical property owing to a change in the physical measurement. We have here a list of examples of principles that are used in sensors. We have the principle of change in resistance. It is used, for example, in a resistance temperature detector. The idea is that the resistance of a material depends on the temperature of the material. For sensors, we choose a suitable material and place it in the material whose temperature we want to measure. We then measure the resistance of that sensor material. From that resistance, we can be able to determine the temperature of the material and therefore the temperature that we desire to measure. A second principle is the principle of generation of a voltage or generation of a current. For example, we use it in a thermocouple. In a thermocouple, we join together two dissimilar metals at one end and leave the other ends open. When we do that, an EMF that depends on the temperature of the junction is going to be generated at the open ends of the metals. Therefore, we can measure this EMF and use it to determine the temperature at which the junction is at, and hence the temperature of the material that we want to measure. In a tachogenerator, the speed at which the tachogenerator is turned determines the voltage that is going to be generated. Hence, we can use the voltage generated by a tachogenerator to determine the speed that we desire to measure. Further principles listed are a change in capacitance, change in inductance, and a change in frequency. For change in frequency, we usually use this in speed sensors. So what happens is the frequency at the output of the sensor depends on the speed at which the sensor is being turned. Therefore, we can use that frequency to determine the speed that we want to measure. Signal conditioning is used to transform sensor outputs into signals that conform to requirements of other components. So generally, the sensors would produce signals of various ranges. But when we design the other components, they usually take signals within certain defined ranges. Therefore, we will need signal conditioners to change from the sensor signal ranges into the ranges that have been designed for the other components. Some examples of signal conditioning operations are signal type conversion. For example, we can change from a resistance into a voltage, or from a resistance into a current, or from a voltage into a current, or current into a voltage as is necessary. Another example, amplification or attenuation. So sometimes the signals are too small. Therefore, we will need to increase their sizes by amplifying them. For example, in thermocouples, we will need to try to amplify them into ranges of volts, because thermocouples produce signals in the range of millivolts. We can also require attenuation. For example, in taco generators, the voltages that may be generated can be quite high. So we may need to attenuate them, reduce their sizes so that they conform to the requirements of other components in the system. We also have got filtering to remove maybe noise, linearizing. So sometimes a sensor produces a signal that is not linear. So we may need some device that makes the signal to be linear so that it is suitable for the rest of the components in the system. Rectification, some sensors may produce AC, so you may need to change the signal into DC. Limiting and clipping is another one. So we may need to cut off some signal excessions so that it suits the requirements of the rest of the system. Generally, operational amplifier circuits are used as signal conditioners. In a number of sensor applications, the sensor and the signal conditioner are built into one unit. That single unit can be referred to as a sensor unit. Sensor units generally are designed to give as output standard output signals. A standard signal is a signal that is at a level that has been agreed upon as the standard for interconnecting equipment in the particular field of application. In instrumentation and control, the standard signal levels are, for discrete signals, when we say discrete signals, we mean those signals that can be either true or false, that is a 0 or a 1. So the levels that we use could be 0 or 24 volts DC, meaning that a 0 is represented by 0 volts and a 1 is represented by 24 volts. We can also have 0 and 220 volt AC. We can also have 0 and 110 volts DC. For continuous signals, the standard levels are a 4 to 20 milliamp signal. So what it means that when the sensor is generating the minimum output, it gives 4 milliamps. When it generates the maximum, it gives 20 milliamps. Other levels, 3 to 15 psi. 3 to 15 psi is used where we are using pressure as a signal. So the lowest will be 3 pounds per square inch and the highest 15 pounds per square inch. We can also have voltages in the range 0 to 10 volts or 0 to 5 volts. Standardizing signal levels enables equipment from different manufacturers to be compatible. So it makes our field of application to be worked with a lot of ease. We don't have to be redesigning some equipment to make it be compatible with with equipment from different manufacturers. The types of applications that we put the sensors to can put the sensors into two groups. These two groups are discrete sensors and continuous sensors. Discrete sensors are those sensors that give an output that can assume only two possible levels. Such sensors are used, for example, to detect the state of a process or to detect the presence or absence of an object. We can use such sensors, for example, to detect whether a conveyor belt is moving or not, whether a machine arm is fully extended or not. Examples of sensors that can be used include mechanical switches, limit switches, and optical sensors. Continuous sensors are sensors that produce a signal whose magnitude varies with the magnitude of the measurement. They can be used to measure such things or such measurements as level or quantity of a parameter. For example, to measure temperature, speed, liquid level, mass, flow rate. Examples of sensors that can be classified as continuous sensors include thermocouples, resistance temperature detectors, a tacho generator, and load cells. Here we've got some examples of discrete sensors. We start off with limit switches. A limit switch is essentially a mechanical switch operated by some arm. The arm is arranged such that it is moved by the object that we desire to sense or to detect. When the arm is moved, it causes breaking or making of an internal conduct. That conduct can be made to be part of an electrical circuit, and therefore it can be used to make or break the circuit. Making or breaking of the circuit can be used to detect the absence or presence of an object that we desire to detect. Second, optical sensors. Optical sensors come as two units. The two units are an emitter of light and a detector of light. The units are placed in a line of sight. When the space between the two units is not blocked, light is able to reach the receiver. When the space is blocked, light cannot reach the receiver. The fact that light has reached or light has not reached the receiver reflects as an output of the sensor, and that output is a two-state output, either a low voltage or a high voltage. The output can thus be used to tell the state of the space between the two units and therefore the state of the object that we desire to determine. Proximity sensors. These are sensors that detect objects when they get within a certain range from the sensor. They use either the principle of inductance or the principle of capacitance. When an object is placed close to the sensor, the changes in inductance or capacitance will result in a change of the output. So the output can switch from high voltage to low voltage, or maybe from low voltage to high voltage. Let's also look at some examples of continuous sensors. We shall begin with a thermocouple and an RTD. Both these sensors are used to measure temperature. They only differ in their principles of operation. In terms of construction, you will find that they've got a similar construction as can be seen on the illustration. Also, these sensors have inbuilt signal conditioners so that generally they give the output as a current in the range 4 to 20 milliamps. 4 milliamps will correspond to the lowest temperature measured by the sensor. 20 milliamps corresponds to the highest temperature measured by the sensor. Signals outside the range 4 to 20 milliamps will indicate some problem or some error in the measuring circuit. The controller or the receiving unit can be configured to tell the user that there is a problem whenever a signal outside the range 4 to 20 milliamps is received from the sensor. Load cells. These are used in the measurement of weight. For example, the weight of a silo that stores raw materials in a manufacturing plant. Another example is the weight of a weigh bridge. Weigh bridges can be found at such places as entrances into and exits from companies. They are used, the weigh bridges will be used to measure usually the weight of haulage trucks on entrance and an exit, so as to tell maybe the material that would have been left into the company or the products that have been taken out of the company. Load cells also have got inbuilt signal conditioning. This makes them to give an output in the standard range, that is 4 to 20 milliamps. Taco generator. A taco generator gives either a voltage whose magnitude depends on the speed that is being measured, or an AC voltage whose frequency depends on the speed being measured. When using a sensor in some application, it is important to match the characteristic of the sensor to the kind of application that is desired. Here are some characteristics that can be used in the determination of the suitability of a sensor for a particular application. We have got accuracy, which is maximum difference between sensor output and actual value. Resolution, the smallest change that the sensor can detect. So the smallest change that you want to detect in the application will determine the minimum resolution you require for the sensor. Repeatability, you have got precision, you have got linearity, we have range, dynamic response, that is the frequency. The output from a sensor also depends on the frequency at which the quantity being measured is changing. So it's important to take note of the dynamic response of the sensor. Environmental limits, then we've got calibration. So how often will you need to recalibrate your sensor also is a factor in the selection of the sensor. Then the cost of the sensor, and cost rises if you desire better precision. So you need to do a balancing act there in terms of cost and precision. We now go into part B of the lecture, which looks at the methods that we use to connect sensors to the receiving circuits or to the controllers. Discrete sensors work by switching on or off circuits in which they are connected. Depending on the particular type of sensor, there are 4 ways in which a discrete sensor can be connected to the receiving circuit. These are the plain switch connection, the sinking or sourcing connection, the TTL connection, and the solid state relay connection. The plain mechanical switch connection is basically a circuit loop that links a power supply and the receiving circuit. In our case, the receiving circuit is a PLC input card. The sensor is connected as part of the circuit loop and in such a way that it is able to close or open the circuit depending on the state of phenomena being measured or being detected. When the circuit is closed, there's a flow of current through the receiving circuitry. When the circuit is open, there is no flow of current through the receiving circuitry. This resulting flow or lack of flow of current through the receiving circuitry is interpreted by the receiving circuit as detection or non-detection of the phenomena that is intended to be detected. The plain mechanical switch connection is used for such sensors as limit switches, ordinary switches, and sensors that have got relay output stages. In our illustration, we have 2 examples of sensors connected using the plain mechanical switch connection. The first one is a normal open push button. This push button is connected between the positive terminal of the power supply and point number 1 on the PLC input card. When the push button is pushed, the circuit is closed and there's going to be a flow of current from the positive terminal of the power supply into the PLC input card through input point number 1. From there, it passes through the internal circuitry that will detect that there's a flow of current and interpret it as a certain state of the condition being measured. From the internal circuitry, the current is going to leave the input card through the common point back to the power supply. The second example of a sensor is a sensor that has got a relay output. This sensor, the sensing part of the sensor, will detect the physical phenomena. Depending on the state of the physical phenomena, the sensing part is either going to close or open the relay output stage. The contacts of the relay output stage are connected between the positive power supply and point number 6 of the input card. If the relay is closed, there's going to be flow of current from the positive power supply point through number 6 on the input card, through the internal circuitry and back from the input card through the point the common point, and eventually to the power supply. When there's no, when the relay output stage is opened, there's not going to be any flow of current through the PLC input card. Just like the plain mechanical switch connection, the principle used in the sourcing and sinking connections is to allow or to stop current flow through the receiving circuit. Sourcing and sinking connections are used to connect those sensors that have transistor output stages. The sensing part of the sensor detects the physical phenomena, and depending on the state of the physical phenomena, turns on or off a transistor output stage. For sinking connection, the transistor at the output is an NPN transistor. This transistor, when turned on, will sink current from the receiving circuit or from the, say, for example, from a PLC input card. The sourcing connection is a PNP transistor at the output of the sensor. The PNP transistor, when turned on, will source current to the receiving circuit. Like we said, if we're using a PLC input card, we'll source current into the PLC input card. Sinking and sourcing sensors are connected to the receiving circuit using either 3-wire connection or 2-wire connection. In the first illustration, we are showing an example where we are connecting a sinking sensor to a PLC input card using 3-wire connection. The sensor has 3 terminals. 2 of the sensors are the power supply terminals. The third terminal is the collector of the NPN transistor output stage. The positive terminal of the power supply is connected both to the sensor and the PLC. The negative terminal of the power supply is connected only to the sensor. The collector terminal of the sensor, that is the collector terminal at the output stage of the sensor, is connected to 0.00 on the PLC. This connection creates a current loop that runs from the positive power supply terminal point through the positive point on the PLC input card, and from there it runs through the internal circuitry of the PLC input card, where it is going to be detected and interpreted accordingly. After that, it leaves through the 0.00 and flows to the collector of the transistor output stage of the sensor. In other words, the collector is going to sink the current from the PLC input card. From the sensor, the current will flow out through the negative terminal and back to the power supply. When the sensing part of the sensor detects the relevant physical phenomena that is being detected, it is going to turn on or off the transistor output stage. In other words, it is going to stop or allow sinking of current from the PLC input card, and accordingly result in detection of the physical phenomena that is being measured. The second illustration shows a situation where a sourcing sensor is connected to a PLC input card using 3-wire connection. The nature of the connection is very related to the way in which a sinking sensor is connected to a PLC input card using 3-wire connection. The differences are that in this case, it is the negative terminal that is connected to both the sensor and the PLC input card, and it is the positive terminal of the power supply that is connected only to the sensor. The loop of current, that is the loop of the current that is used to detect the presence or absence of the phenomena being measured, that loop runs from the positive terminal of the power supply point, goes into the sensor through the positive terminal, and it leaves the sensor through the collector terminal of the PNP output stage transistor. In other words, the sensor sources current. From the collector of the output stage of the sensor, it goes into the PLC. Then it leaves the PLC through the common point back to the power supply point. So in this case, the sensor will make the output stage of the sensor to either allow or stop sourcing of current into the PLC input card. The third illustration shows a situation where a sinking sensor is connected to a PLC input card using the two-wire connection. For two-wire connection, and for the case of a sinking sensor, the collector point on the output stage of the sensor is joined together with the positive terminal of the power supply to produce a single terminal in the diagram labeled as V+. This terminal is connected to the positive point on the power supply. The negative terminal of the sensor is connected to an input point on the PLC input card. The negative terminal of the power supply is connected to the common point or to the negative point on the PLC input card. So the loop of current runs from the positive terminal of the power supply and goes to the sensor through the positive terminal. It leaves the sensor through the negative terminal and goes into the input point on the PLC input card. From the PLC, it goes into the power supply and it leaves the PLC through the common point. We can observe that the sensor as a whole acts as a component that is going to limit or allow the flow of current in the loop. When the output stage transistor is turned off, there is a small current, a very small current that flows in the loop. That current is enough to operate the circuitry inside the sensor because that circuitry will require power, but it is small enough not to be detected as a flow of current by the PLC input card. When the output stage is turned on, a significant current flows in the loop. That current is enough to be detected as a flow of current by the PLC input card. So the difference is in the magnitudes of these two currents when the transistor is on and when the transistor is off are the ones that are used to differentiate between the two states of the physical phenomena that is being detected by the sensor. For the case of a sourcing sensor, the arguments are the same. The difference is that for a sourcing sensor, the collector terminal on the output stage of the sensor is joined together with the negative terminal of the sensor to produce a single terminal in the diagram labeled as V-. That terminal is connected to the power supply, negative point. Then the positive point of the power supply is connected to the positive point on the PLC input card. The positive terminal of the sensor is the one that is connected to an input point on the PLC input card. Every other argument applies the same, only being careful to sometimes reverse currents or reverse the positions of components to suit the sourcing sensor. The TTL connection is used for sensors that give TTL outputs. So TTL outputs are those signals that can either be 0 or 5 volts, depending on whether it is a 1 or it is a 0. Such sensors would need the controller to have a TTL input interface module. Then solid state relay connection is used when there's a need to interface with AC signals. Continuous sensors are connected to receiving circuits using either the single-ended connection or the double-ended connection. In single-ended connection, the return wires for all the sensors are connected together and to a common point on the receiving circuit. For example, in our illustration there, sensor 1 labeled as device 1, the positive terminal is connected to input 0. The positive terminal of device 2 is connected to input 1 on the receiving circuit. Then the negative terminals are connected together and connected to the common point on the receiving circuitry. For double-ended, each device, each sensor has got two terminals, one for the negative terminal and the other one for the negative terminal. So we can see that in double-ended, we can reduce the interference between signals from different devices. A continuous sensor can be connected to the receiving circuit using either a twisted pair or using a shielded cable. Twisting pairs of conductors reduces noise induced by magnetic fields. The principle that works there is that the pairs will pick the same amount of noise. When we get to the end of the pairs, we get the signal difference between the two pairs. Using suitable electrical circuits, we therefore can reject the noise that would have been picked by the twisted pair. In shielding, we apply a shield around the conductors that carry the signals. This shield will reduce the amount of electromagnetic interference that gets to the signal conductors.